right, great. Well, good afternoon, everyone. My name is Dr. Bradford Johnson, and I'm an assistant professor in the Department of Geography, and you're joining the Florida State University's Department of Geography Spring Colloquium Series. And today I have the pleasure of introducing to you Dr. Neil Debbage, who will be coming to you and give you an idea of what to expect this afternoon. Dr. Debbage will talk for about 55 minutes to an hour, and then we'll have a Q&A session following that. So to give you an idea of what to expect during that, if you have a question that comes up, please feel free to utilize the Q&A button. You should notice it at the bottom of your Zoom interface. If you use the chat, we may miss it, so make sure you put any questions into the Q&A section instead. We will hold all questions until after Dr. Debbage has completed it, but again, so the questions are fresh in your mind, feel free to go ahead and ask those at any point, and we'll keep track of them until the Q&A session later on. Other than that, I'll go ahead and introduce Dr. Debbage. He's actually an assistant professor of geography and environmental sustainability at University of Texas, San Antonio. His research focuses on urban climatology, natural hazards, and sustainability. Specifically, Dr. Debbage utilizes GIS, statistical modeling, and numerical weather modeling to better understand how cities and their residents can become more resilient to heat and flood threats. His past research projects have studied the urban heat island effect, while his ongoing work analyzes both the physical and social factors that influence urban flooding vulnerability. Dr. Debbage's research has been published in Water Resources Research, Computers, Environment and Urban Systems, and the International Journal of Climatology, and appeared in a number of news outlets, including NPR and the Weather Channel. He was recently appointed by the City of San Antonio to serve on the Technical and Community Advisory Committee, which is tasked with guiding the implementation of the city's Climate Action and Adaptation Plan. Dr. Debbage is a triple dog in that he's received his PhD, MS, and BA in geography from the University of Georgia in Athens. Please join me in a virtual round of applause in welcoming Dr. Neil Debbage. Thank you for joining us today, Dr. Debbage.
Thank you, Brad, for the very kind introduction. I'm really excited to get to first meet with several of you today and then also share some of my ongoing work. So I'll go ahead and pop it into screen sharing mode. And Brad, if you could just confirm one last time that you are seeing this correctly. I don't want the whole presentation to go by with no one seeing anything. So is it showing up well?
Loud and clear and visually good.
And the slides are going?
Yes, sir.
All right. All right, so thank you all for attending today. It's really been a pleasure to get to meet some of you throughout the day. Of course, I do wish I was there in person and enjoying some of the warm Florida weather. It's even gotten cold all the way down here in San Antonio. But nonetheless, it's been great to get to know more about your department and the type of research that your faculty and graduate students are doing. I also want to extend a special thank you to Brad as well for organizing this event over the past, I guess, several months at this point since the original invitation. So thank you for kind of making sure I'm taken care of and understanding all the ways we'll be interacting virtually. So with that, I wanted to share some findings from an ongoing project, which is really looking at how urbanization and hydrometeorology interact with one another and how both of those can act to influence urban flooding vulnerability. And in particular, this phase of the research will focus on the Charlata megaregion. So that's what we're looking at here, the downtown connector going through downtown Atlanta. You might notice the Georgia Dome that is no more off here to the right. So we're really going to be thinking about how the urban environment influences hydrometeorology, as well as the impacts that that can have on the residents in these cities and how those impacts might not be equal across different communities. So just to give us a little bit of a roadmap in terms of where we'll be traveling over the next 45 minutes to an hour or so, First, I wanted to introduce you all to a broader research framework and position this talk within it, so you have a general sense of kind of where this fits in with some of my other projects. Then I want to share two specific examples of how urbanization is impacting hydrometeorology and flooding vulnerability. Now, the first example will focus on something called the urban rainfall effect. And in particular, that first example involves a case study of the very large flood event that occurred in Atlanta in 2009. So trying to understand how the urban environment influenced that flooding event. And then the second example, we'll look at, well, when we do have these large floods happening, who's actually at risk and who's bearing potentially a disproportionate burden in terms of urban flood risk. So this gets into the realm of environmental justice and climate justice research. And then finally, I want to show a few avenues of where this is going, right? So where are these research projects heading in the future? So just wrapping up by touching on future research directions. Now, like I mentioned, I wanted to start it off with the research framework and how this is all positioned. So at the broadest sense, I consider myself a geographer that's really interested in human environment interactions. Now, on the one hand, spent quite a lot of time thinking about humans, primarily how they influence the environment, that is, primarily through things like urbanization and land use change and how that impacts certain elements of the natural environment, like the climate system, stream flow patterns, and things of that nature. So that's one big sphere of inquiry that I spend quite a bit of time thinking about, writing about, and kind of doing data analysis in. And these types of projects have focused on things like the urban heat island effect, the urban rainfall effect, which we'll talk about a little bit more today, and urban implications for stream flow regimes. Now, I'm also interested in this other direction, which is how the environment, primarily through things like natural hazards and climate hazards, impacts humans, primarily people that reside in cities. So how do these environmental hazards impact urban communities, and how are these impacts potentially vary depending on the specific community that you are discussing? So really, I'm interested in this multi-directionality between human environment interactions, and I'm really excited to get to share some of this work specifically with your department, because it seems like in terms of the faculty and what your graduate students are doing, you cover a lot of this breadth, and it really is one of the great strengths, I think, of the discipline of geography. Now, of course, there are some things that unify these two different directions of research. The first is an emphasis on quantitative geospatial techniques. So my work relies heavily on geographic information systems, R, geospatial analysis in Python, and as well as numerical weather modeling. So all those techniques are applied on both of these directions. And they also share an emphasis on urban resiliency and policy. So the underlying motivation behind a lot of this work is to understand these interactions better so we can inform land use policy, emergency management planning, and other policy measures to help, one, reduce the impacts that urbanization might have on the environment, and then two, to enhance the resiliency of those communities that could be feeling those impacts within cities. So this broad framework is motivated by several factors. So it's motivated by demographic trends, and it's also motivated by climatic trends. So some of you might be aware, over half the world's populations already reside in urban areas. So that's what we're looking at here in the bottom left. We can see around 2005, the majority of individuals now reside in urban areas, and that trend is only projected to continue to grow, with more and more individuals moving to urban centers, which suggests that we'll have more urban expansion in terms of impervious surfaces, which will only enhance the impacts on the environment moving forwards. And it also suggests that we might have more individuals within these urban centers residing in areas that are prone to hazards like flooding and heat as well. So we have this demographic trend that really showcases the importance of trying to understand urban environments. Now, on the other hand, we know we have ongoing climate change, which has increased the frequency and intensity of several different types of extreme events. So for example, we know we're seeing more extreme precipitation events. We're seeing more frequent and extreme heat waves. And these pose particular challenges to urban environments because we know urban environments are already inherently vulnerable to these types of hazards. So if they're becoming more extreme and potentially more frequent as well in coming years, this is a less than ideal situation for our urban centers where we're concentrating more and more people. So overall, these two trends threaten the sustainability of urban environments. So the goal of much of this research is to try to understand how we can make urban environments more sustainable and also enhance the resiliency of people residing in these urban environments. Now, the other element of these specific examples is that they will focus on the Charlata megaregion. So you may have heard of the Charlata megaregion, or you may not have, but it's basically an urban region that extends along the I-85 corridor, which you can see here in the red line. So we have the I-85 corridor throughout Georgia, South Carolina, and North Carolina. And along that corridor, we have several metropolitan statistical areas, or MSAs. So we have Atlanta, Greenville, Spartanburg, and then Charlotte. So this is the primary area that this research will really be focusing on. And part of the reason this is a really interesting area to analyze is because these urban environments are becoming more and more interconnected. Of course, the I-85 corridor physically connects these cores, and we're seeing the continued expansion of the urban environment, kind of like tentacles expanding out towards one another, which again suggests we could see more impacts on the environment and potentially more individuals residing in areas that are at risk to various climate hazards. So like I mentioned, we're really interested in this Charlata megaregion due to its large, sprawling urban footprint. All projections suggest that it's going to continue to expand. So Tornado et al. Ran a really nice urban growth model showing these areas of fairly rapid expansion within the Charlata megaregion as the individual cores will continue to grow together and coalesce. And this has two implications. One, it suggests that we'll likely have further increases in flood zone occupancy. So we have more and more urban development occurring. It's likely that we'll see more and more individuals residing in areas that are at potential risk for urban flooding. And a really great study by Ferguson and Ashley here has highlighted that quite well in the sense that we can look at these housing unit density. So this is the Atlanta metro area. So Fulton County's the urban core. So downtown's roughly right here. And we can look at how housing unit density, specifically in the flood zones, has changed over time. So what we're looking at are the darker greens being greater housing unit densities in the flood zone. And you can see, well, of course, the most urbanized area has the greatest housing density in the flood zone. But over time, you can see that those greens are getting darker, which essentially means even in the urban core, we're having more and more people in housing units added to the flood zone. So that's one trend we can see. But you also might notice that even along the periphery of the MSA, so kind of this ring around what we might consider the urban core of the metropolitan area of Atlanta, we can see the quantity of housing in the flood zone is expanding in these regions as well. So it's not only an amplification of people living in flood zones in the urban core, but a continued increase in the more peripheral regions along the edges of the MSA. So we have this continued growth, which means we likely will see, and this study suggests we do see more people residing in areas at risk for flooding. Simultaneously, we also know that if we're seeing this urban growth, that means more impervious surfaces, which can have impacts on flood intensity and frequency as well. So it's kind of this double whammy effect. And that brings me to the first specific example I wanted to spend a little bit of time discussing. And remember, this is the one looking at the 2009 Atlanta flood and trying to understand the complex role that the urban environment played in potentially governing the runoff and the initial amount of precipitation during that event. So what you can see here is the Four Seasons Park. I don't know if anyone's traveled up to Atlanta to go to the Six Flags amusement park. It's right on the banks of the Chattahoochee River, which is right here, kind of along the top. And you can see the Chattahoochee River during this flooding event easily spilled over its banks and flooded the roller coaster. It flooded large portions of the metro Atlanta region. So this 2009 Atlanta flood occurred due to prolonged rainfall between September 16th and September 22nd. In terms of the maximum 24-hour rainfall total that was observed, it exceeded 20 inches, and that occurred on September 21st in Douglas County, which is just west of Fulton County, actually quite close to where the Six Flags amusement park is. Now, we can also look at the stream gauge data. So that's what we see here on the right. Now, the blue lines are the stream flow during the flooding event. The pink solid line is the record before this event, and the dotted pink line is the 100-year storm event. So what you can see is that in all these gauges throughout Douglas County and around Douglas County, the event was pretty significant. So we can see it exceeded most of the records, or it at least exceeded a 100-year event throughout the region. We can also notice that the shaded blue areas when the gauges were broken. So the flooding was substantial enough to actually break the stream gauges and other meteorological observation equipment during the flooding event. Now, in terms of societal impact, there were unfortunately 11 fatalities attributed to the flood, and the damage claims approached $220 million. So again, a very substantial flooding event, which really highlights the vulnerability of these urban environments to flood hazards. So that's kind of a bit of an overview in terms of what it was and when it happened, but what caused it to happen? What caused this significant flooding event throughout the Atlanta metro area in 2009? There's actually several different meteorological processes that contributed to the flood that were identified by Shepard et al. In 2011. The first feature that they noted was the weak cutoff low, which actually stalled over the lower Mississippi Valley before the event on September 17th. And this weak cutoff low essentially helped create moist antecedent conditions. So it we already had some saturation of the soils and things like that. So obviously that kind of primes the pump for a more severe flooding event down the road, which is exactly what we saw. Now, in terms of the surface flow, which is what we're looking at here at the bottom left, this is a surface analysis map leading up to the event. We had persistent southerly and easterly flow throughout the event, and that was associated with the low pressure center roughly over Louisiana. So we have that counterclockwise rotation spinning up moisture into Georgia, I guess over Tallahassee, right? And into Georgia from the Gulf. So plenty of moisture source from that direction. Then we also had this blob of high pressure in the Northeast and the clockwise flow around that, pushing in moisture into Georgia off the Atlantic. So essentially during this event, we're tapping into both moisture sources at the same time, both the Gulf and the Atlantic, and it's kind of colliding in Georgia, and specifically very close to the Atlanta metro area. So again, that gives us very high precipitable water values that are often conducive to large flooding events like the '09 flood. So that's the situation at the synoptic scale. Now at the mesoscale, throughout the event, we did have training which occurred, and that contributed to some of the highest rainfall totals. So basically, we have the storm propagating and backbuilding at such a rate that we have storms forming over the same area over and over again, which obviously can enhance the rainfall. And then finally, there was a hypothesis in this 2011 paper that urban enhancement may have also played a role. Now, the reason this was hypothesized is because if you see in the figure on the right, the bright reds and pinks are where most of the rainfall occurred. And we can see that that is actually occurring downwind of the urban environment. So something that is a little unique about this situation is that usually downwind would be, of course, off here to the east because we have westerly flow. But like I mentioned, during this event, we had basically southeasterly flow, southerly flow, easterly flow, kind of southeasterly flow overall. So the downwind area is actually in this exact same pocket where we saw the greatest rainfall totals. So the idea here is that it could be, it's lining up at least spatially with where we would expect this urban enhancement to occur, because the literature suggests that typically manifests itself downwind of cities. So spatially, it seems like that could have been a factor as well. So the overall goal of this project was to try to more quantitatively evaluate this hypothesis, right? Can we actually get in here and figure out, did the urban environment contribute to this spatial pattern, or was it a bit more just happenstance? So it's probably worth spending a little bit more time explaining the urban rainfall effect or urban rainfall enhancement and how this actually happens and the history behind this idea in terms of why it was hypothesized as a potential factor during the 2009 Atlanta flood event. Now, the urban rainfall effect isn't really new. It dates back really to the 70s in the Metromex, which is the Meteorological Metropolitan Experiment, where they basically went around and studied several different cities and identified that we indeed saw an enhancement of warm season precipitation due to urban effects. So this idea, if you look at kind of the summertime where you don't have much synoptic forcing, the urban environment can indeed enhance precipitation. Now, since those initial studies, quite a few additional studies have been done, which really acted to better identify the specific mechanisms and really confirmed a lot of the initial hypotheses put forth by the Metromex project. So now we have a list of several mechanisms that we know can contribute to this urban rainfall enhancement. Now, the first is related to the urban surface roughness, where we can see enhanced surface convergence. So the idea here is that if you have winds, looking here at the bottom left, they will bifurcate potentially around the city, and then downwind, they will come back together, or in other words, converge. And whenever you have convergence, that can help prompt upward motion, which is a key ingredient to precipitation and storms. So that's one hypothesis or one mechanism that we often see is the surface roughness enhancing convergence. The other has more to do with heat, where we know cities are typically warmer than their surrounding environments. So if you have this pocket of warmth over the city, that creates what we call an urban heat island circulation. So it is essentially a localized low pressure and buoyant area over the city, creates this buoyant motion and rising motion over the city. So we have this unstable pocket of air, which is again conducive to creating precipitation. And then the third broad mechanism that we suspect could be influencing these urban rainfall enhancements are aerosol concentrations. So we have quite a bit of aerosols in urban environments, so particulate matter due to all the urban activities. And these aerosols play an important role as cloud condensation nuclei, so they're very important in cloud physics and rainfall processes as well. So that's kind of it's a more complex mechanism, I think it's safe to say, but definitely another mechanism that's influencing this urban rainfall enhancement. Now, some more recent studies have also continued to highlight this urban rainfall enhancement. On the left, we have a really excellent graphic from Louis and Nyogi, who basically did a meta-analysis of around 100 urban climate studies to try to quantify on average what this urban enhancement actually is. So to put some numbers on it. So they looked at all these studies. They found that downwind of the urban environment is where we see the greatest enhancement. So enhanced by around 18% on average. We also see a little bit of an enhancement over the urban core. So around 16%, and then much more marginal enhancements upwind and on the sides of the city. So again, showcasing that this is fairly widespread. And more recently, people have continued to look at Atlanta as well. So McLeod et al. Did some really interesting work with precipitation climatologies. So you can kind of almost see this plume, so the yellow and orange and red plume downwind of Atlanta in the precipitation climatology, where you can see this downwind amplification. Something that they really pointed out that was pretty interesting and novel was this whole idea of flow dependency, so flow regime dependent plumes, which is the idea that, of course, the plume shows up over here throughout the entire climatology, since on average, or on most days, we have westerly flow. But if you look at other days where the flow maybe is southerly, they basically showcased how this plume can move around according to that predominant flow regime, which is again kind of important for the 09 flood because it doesn't really match up with this climatology because the flow was southeasterly and not westerly. So in terms of the specific research questions we are hoping to address in this first study, we wanted to look at how the urban environment influenced the spatio-temporal characteristics of 1, runoff, and 2, precipitation during the 09 flood. Then the next step was to try to understand, well, if we do see any alterations, can we at least hypothesize what mechanisms might be responsible for these enhancements or alterations of things like runoff and precipitation. And the big overarching question that we were really hoping to address is understanding if urban environments can influence precipitation during heavy rainfall events with prominent synoptic scale forcing. So a lot of the urban rainfall effect research that's been done focuses on warm season precipitation or the summer, since synoptic forcing is less pronounced. It basically makes it easier to try to tease out the potential urban influence. So looking at a big flooding event gives us an opportunity to see if those mechanisms can also play out when we have pretty pronounced synoptic forcing as well. So of course, the argument here is not that the city was the primary cause of this flood or the rainfall, but was an important secondary player in terms of governing where we see some of these pockets of most intense rainfall. So in order to do this, it's a bit challenging to tackle those types of questions with observations alone due to the complex interactions between the urban environment and the atmosphere. So we leaned upon WRF, which is basically a numerical weather model developed primarily by NCAR and NOAA. It's a non-hydrostatic model, and it's been used pretty widespread for things like urban flooding studies and urban studies in general, or anything that's really best analyzed at the mesoscale. So essentially the way this works is you input some land use data, you input some gridded climate data, that gets interpolated over the model domain, both horizontally and vertically. So you imagine it's basically like a Rubik's Cube, right? Where you have a two-dimensional and, well, really a three-dimensional grid, and you're solving equations to resolve atmospheric motion, precipitation, and a whole host of other atmospheric characteristics over time. So this is basically the tool we use to try to answer some of those questions. Now, whenever you're running WRF, you have a large number of configuration settings you can specify. So for our model run, we use a two-way nested model covering a majority of the Southeast. So we have two domains. We have our outer domain, which covers a big portion of the Southeast, and then our more detailed inner domain, which begins to zero in here on the Atlanta metro area. In terms of the climate data, we used NAR to initialize the model and provide the boundary conditions throughout the model run. So we selected NAR due to its slightly higher temporal resolution, so we could continue to update the boundary conditions. And you can see some of the other specifications here. So we ran the model for around 10 days. We started it a bit before the actual flooding event, so we had plenty of spin up time. The outer resolution was 10 kilometers, and then the more detailed inner domain resolution was 2 kilometers. And you can kind of take note of the different physics and microphysics parameterizations. We can talk about that more during Q&A if you're interested. The cumulus physics parameterization ended up being pretty significant. But again, we won't dig into all those details now, but feel free to ask if you're interested. Now, of course, to look at the urban environment, we basically did two runs. We did an urban run with the city, and then you can take the city out and see what would happen if all that urban land cover was just natural vegetation. So for the urban run, we actually replaced the urban land use, which is from MODIS, the default urban land use within WRF, with a more detailed urban land use. And specifically, we used the NLCD. So instead of having one general urban class, we have these three more detailed urban classes in shades of red and pink. We also specified the urban fraction explicitly on a per pixel basis rather than using a lookup table, and that was also done using NLCD data. And then we also used a single layer urban canopy model to more realistically depict the transfers of momentum and energy within the urban environment. Now for the non-urban run, all that obviously was pretty much irrelevant. We basically just replaced the urban cover, which you can see in the red, with a cropland natural vegetation mosaic. So you can basically see kind of this, I guess, khaki brown color, how the urban environment has essentially been masked out in the non-urban run. Now, once we do the urban and non-urban run, we can look at the output and basically look at the differences between the two. And much of this analysis focused on the period of peak rainfall, which was September 19th through 22nd. And to start off with the analysis, we compared with some observations to try to get a handle of how well the model was performing. So we compared the model output with the MPE, which is basically a gridded precipitation product that combines radar and Gage data. We also looked at some actual Gage data. So the ASOS station at Fulton County Airport, which is roughly right here, this little tiny quadrant of Fulton County, outside of 285, but north of 20 is where that station is located. And then we also looked at Coco-Ross gauges within this area downwind, where we were really particularly interested in looking at precipitation values. In terms of the other steps in the analysis, we created difference maps to essentially look at changes between the urban and non-urban runs. And then we calculated aerial averages to look at specifically how the precipitation in this box downwind, where we hypothesized urban enhancement occurred, how that varied between the urban and non-urban runs. One of the other really cool things about WRF is you don't have to look at just output at the surface, but you can look at what's going on vertically. So we looked at several vertical cross sections, which were conducted along these two transects. And I'll show you one cross section from this red transect today, which is just north of I-20. So what did we find? Well, first we just mapped the precipitation from our WRF urban model and the MPE. So remember the bottom here is basically a combination of Gage data and Doppler radar data to estimate precipitation. And here at the top, we have what the WRF model run was suggesting. Now, of course, it's not a perfect representation, but you do see some of these notable features where we have this finger of intense precipitation right here just north of I-20, which is being depicted fairly accurately. We do see these two other clusters in northwest and northeast Georgia showing up in the model run. The second time step or the second day, we see a similar trend where it kind of matches up with this pocket of intense precipitation over and downwind of the city. And again, a rough correspondence in the third day as well. Now, what you might notice is we do see a bit higher totals earlier on in the WRF model run, which suggests it's initiating the precipitation slightly earlier. Now, to complement just those visual comparisons, we compared the actual values of precipitation in that downwind box with several of those measures I mentioned earlier. And this does showcase that earlier initiation that I was discussing in the model. So the model here is the black line, and then our other observations are the blue, green, and gray lines. So we see this earlier initiation. But in terms of the overall totals, you can see that the WRF model aligns pretty closely with the NPE and the CoCo-Ross averages. And the only reason the ASOS station at Fulton County Airport is so low is because the gauge actually unfortunately broke right here during the storm event. So we can see the overall totals were depicted fairly well. The timing maybe was slightly off. We quantified the root mean square error and found that it was generally comparable to the RMSEs of other studies. So we were happy to see that. And we also found that the root mean square error for the urban simulation, so when we included the city, was lower than that of the non-urban simulation. So including the city helped improve the model run, which is what we would expect because the city is actually there in reality. So once we were happy enough with the specifications of the model and its performance, then we can kind of start to compare and contrast the urban versus the non-urban runs. And what you can begin to see, so again, here on the top is the same urban graphs we were looking at before, but at the bottom, we're looking at the WRF run with no Atlanta in it. And you can see that we don't really have this pronounced little finger of intense precipitation downwind of the city develop as notably in the non-urban run. The second day, we see that really over and downwind of the city is almost like a hole in terms of having lower precipitation values compared to what we saw in the urban run and in the observations. And again, in the final day, we have less precipitation over the urban environment in the non-urban model. So visually, this begins to suggest that the urban environment could have been playing an important role. We can quantify this a bit more by looking at just the downwind box and averaging across it. So in that downwind area of interest, the non-urban model underestimated precipitation by around 100 millimeters. So you can see urban, again, is the black line, non-urban is the gray line, and you can see that it is grossly underestimating what actually happened downwind of the city. So remember the WRF model was up here and most of the observations were up here as well in terms of the total precip over these two phases of the flooding event. So this begins to really suggest that the urban environment influenced the location and quantity of precipitation during the flood event, which again is beginning to suggest also that the urban environment can still play an important role even in these synoptically driven events. So then the next question is, well, what maybe caused this? Well, we have a lot more impervious surfaces, so we can look at the difference in surface runoff. And we can see, of course, that we have much greater surface runoff in this area of intense precipitation downwind on day one, and much greater runoff over the city in the urban model compared to the non-urban model on day two. So this is likely a combination of the enhanced rainfall in the urban model as well as the impervious surfaces in the urban model. So clearly the urban environment is enhancing runoff through those two mechanisms. Now for the rest, we'll really showcase this day in terms of what's happening and why we suspect the urban environment influenced the precipitation totals. And what we saw was a or a distinguished and well-pronounced boundary form downwind of Atlanta in Douglas County, which is where we saw some of those really extreme rainfall totals. So the red pixels are roughly urban Atlanta. And at this downwind urban-rural interface, you can see how the wind directions are kind of slamming into each other, which is basically downwind convergence. So you can see the flow somewhat bifurcating around the city and this pronounced convergence area in the downwind region, which is generally absent in the non-urban run. So again, this is highlighting the importance of surface roughness and how that alters wind flow regimes and can potentially enhance downwind convergence, which looks like what occurred on this first day. Now we can actually quantify the convergence and divergence, and we again see these ribbons of pronounced convergence downwind of Atlanta, which are largely absent in the non-urban model here on the right. And these ribbons of convergence were also much more persistent in the urban run. So it's not just the fact that they were there and not there in the non-urban run, but the fact that they were there, well pronounced and fairly persistent and stationary at the downwind urban rural interface. So of course, why does all this convergence matter? It can help boost vertical velocity. So if we look at the transects, we can see that the the vertical velocities at that basically kind of near that finger of intense precipitation just north of I-20 were much stronger and much more pronounced in the urban run compared to the non-urban run due to that sustained area of convergence at the downwind urban rural interface. So that's just that first day. We can talk about the second day more in Q&A if people are interested in what happened then. But just to kind of wrap up with what all this means, one, we of course saw that the urban environment increased runoff by around 100 millimeters, so pretty substantially. We saw that the rainfall was also enhanced downwind of Atlanta by around 100 millimeters when we compare the urban to the non-urban model, which suggests that the urban environment played an important role in influencing the location and magnitude of precipitation. And the importance of that really in this case is that we're seeing that some of these mechanisms that have been widely documented and studied during kind of warm season environments with weak synoptic forcing can also manifest themselves during a more synoptically driven event. And it also highlights this two-pronged vulnerability of urban environments to extreme rainfall. So I think it's pretty widely known that urban environments are vulnerable because of impervious surfaces enhancing runoff, but this study is suggesting that, of course, that's an issue, but the urban environment might actually be enhancing the precipitation in the first place during some of these flooding events as well. So that is the first example I wanted to share with you. Now, the second example, now that we kind of see the hydrometeorology of this flood event, we can think about, well, who's actually in harm's way? Who's being impacted when these types of flooding events do occur? And in this analysis, we were looking at the Charlata megaregion again, but trying to understand how those risks might be disproportionate across various communities. So of course, this work is really leaning upon an environmental justice lens, and environmental justice really is a complex term because on the one hand, it refers to this local grassroots movement that has dedicated time and energy to mobilizing and taking action in the face of environmental inequities. So historically, a lot of these efforts have been minority communities mobilizing to resist locally unwanted land uses. So things like landfills or petrol refineries, like we can see here in Houston on the right, and trying to address how these are inequitably distributed spatially across the landscape. Now, of course, as these movements gained more and more traction, environmental justice became recognized more formally as a policy. And this led the EPA to define environmental justice as the fair treatment and meaningful involvement of all people, regardless of race, income, and other socioeconomic elements in terms of environmental policies and protection against things like locally unwanted land uses. Now, more recently, this environmental justice framework has been adopted to analyze the potential disproportionate exposure of vulnerable communities to urban flood hazards. Within the American context, at least, this sphere of research really can be traced back to Robert Bullard's seminal work during the aftermath of Katrina, where he analyzed the disproportionate impact of the flooding in areas like the lower Ninth Ward, which we can see here on the right, as well as the additional layers of challenges that these minority communities were facing during the recovery efforts. So it's not just the disproportionate impact, but how people are impacted disproportionately throughout the recovery from these types of major urban flooding events. Now, that work in New Orleans led to several scholars looking at urban flood hazards and potential inequities in a whole host of coastal cities, including New York, Miami, Houston, Tampa Bay, amongst several others. Now, unfortunately, this EJ-informed flood hazard research has often produced inconclusive findings regarding if more vulnerable communities are indeed disproportionately exposed to urban flood hazards. And this is likely due to a whole host of different reasons, but it's at least partly due to the different density mapping techniques that are used to estimate urban flood zone populations. It's partially related to the different scales at which the analyses are conducted, and it's also probably influenced by the local context of the individual cities that are being analyzed. And one really important element is the presence of water-based amenities. So this is the whole concept of water as a hazard or water as an amenity, and how that subsequently influences things like property values and who might be residing near water. On the right, we have a really a great graphic from Mante and Morocco. They basically looked at a lot of these questions throughout the boroughs of New York City, and we can see the risk ratios here. So if the risk ratio is greater than 1 or above the dotted line, that means that group is disproportionately at risk for urban flooding. And if it's level with 1, that means the burden is shared proportionally. And what you might notice is if we look at these different groups, it really depends on a borough by borough basis in terms of what group bears a disproportionate exposure to flood risk. So this really highlights some of the complex geographies, even just within New York boroughs. So in this effort, we're trying to assess the overall magnitude of any socioeconomic inequities and urban flood risk throughout Charlata. And a sub-goal here was to think about how these results might be sensitive to the density mapping issues, the spatial scale issues that I discussed earlier. So we're looking at the Charlata megaregion. You already saw this graph, but I wanted to reintroduce Charlata in terms of its relevance to environmental justice research and why we kind of selected it for this study. The first reason is because it's non-coastal. Like I mentioned, coastal cities have been studied a bit more. So we wanted to see how these issues play out in a non-coastal setting. Of course, we know segregation has shaped the development of all these cities along the I-85 corridor. So it suggests that we could see some substantial inequities in urban flood risk. And then by looking at multiple MSAs, that helps us make comparisons and understand how systemic these types of issues are, or if they're more localized in nature. Now, to address this research, of course, we need to first define which areas are at risk. And to do this, we use the National Flood Hazard Layer, which is maintained by FEMA. This is basically a digital database that defines the flood zones that are used for things like flood insurance. So specifically in this study, we looked at the 500-year flood zone, which you can see incorporates the blue and orange areas. So we basically considered the 500-year flood zone. If you're in that, you're at risk to flooding. Of course, there's limitations with that perspective, which we can get into during the Q&A if you would like, but there's also some advantages as well. Now, once we know the areas that are at risk, we have to define who lives in those areas. So as you likely guessed, that requires us to collect data from the census. So we use the 2010 decennial census as well as American Community Survey data to basically describe the socioeconomic characteristics of the populations living in the flood zones. And we looked at 3 different dimensions. So we looked at race, ethnicity, and poverty. So we were looking at kind of non-Hispanic Black populations versus non-Hispanic white, which is our race dimension. Looked at Hispanic versus non-Hispanic, which is our ethnicity dimension. And we focused on those because those are the primary or largest ethnic and racial minorities in the metro area. And then we also included this income dimension to see how existing economic processes were playing out and if they were more or less important than the racial and ethnic dimensions. And I should mention this was all collected at the census block group scale, which is what these black polygons are on the right. So you have a sense of kind of the spatial size of those. Now, of course, it would be pretty easy if the flood zones matched up with the extent of the block groups perfectly, but of course that's not the case, which means we have to do some sort of asymmetric mapping technique to try to estimate the flood zone population. Now, since we wanted to understand how this could impact the results, we explored 3 different approaches going from like pretty rudimentary to slightly more nuanced and sophisticated. So the first approach is just aerial weighting. So the idea there is if 50% of the block group is in the flood zone, we assume 50% of the people are in the flood zone. So you can probably already see how that has shortcomings. So in this example here on the right, we have our aerial weighting area in red, and you can see it includes a lot of uninhabited natural landscapes, golf courses, and things like that. So there's a good potential you'll overestimate who resides in a flood zone using that technique. To address that, we did an urban filtered aerial weighting where the idea is the same, except instead of using the entire area, you just look at the urban area as defined by the 4 National Land Cover Database urban classes, and that corresponds to this yellow area. So you can see it throws out things like forested areas, but it still includes golf courses, which could again pose some issues. And then finally, we had the most restricted technique, which is to just include the area that is low, medium, or high intensity development to kind of address this issue with the least intense class within the NLCD. Now, we evaluated the accuracy of each of these techniques using the normalized root mean square error and comparing our block group estimates with block level estimates. So in this case, we're using the more detailed block level geography as our kind of quote ground truth. Now, of course, once we have the population living inside and outside the flood zones, we need some sort of statistical mechanism to try to quantify if communities are bearing a disproportionate burden. And to do this, we relied upon risk ratios. And we modeled our risk ratios after the Comparative Environmental Risk Index, which is fairly widely used and developed by Harner et al. And we calculated these risk ratios at several different spatial scales, again, to try to get a sense of how widespread these issues are. So we can look at the whole megaregion as one entity. Then we looked at individual MSAs as cohesive entities, then the individual counties all the way down to census tract level. And we also looked at lake versus non-lake subsets to try to get a little bit of a handle on this water-based amenity issue. So you can see we calculated 3 different risk ratios, one for race, one for ethnicity, one for poverty. Long story short, if the risk ratio is greater than 1, that indicates that the more vulnerable groups are disproportionately at risk to urban flooding. Now, in terms of the accuracy assessment, that was the first element of the methods in terms of trying to assess how these different asymmetric mapping techniques performed. Basically, we saw that aerial weighting, as you probably guessed, overestimated the non-Hispanic white population that resided in the flood zone. So you can see this is our 1-to-1 line, and a vast majority of the points are above that 1-to-1 line. So again, not great, and that poses implications in terms of if you calculated risk ratios just using simplistic aerial weighting, you'd probably get vastly different findings. In terms of the urban weighting versus the low-high urban weighting, the urban weighting, which included all the urban land uses, actually performed slightly better. It had the lowest NRMSE, so that was basically what we used for all the subsequent findings. We used that asymmetric mapping technique. Now, in terms of what we actually did find, we found that more vulnerable populations were between 14 and 42% more likely to reside in the 500-year flood zone. So we can see the risk ratios for all 3 were significant and greater than 1. We also can see that the risk ratio for our poverty dimension, even though it was significant, had a smaller magnitude than our racial and ethnicity risk ratios, which again starts to suggest that kind of the economics of this question is more of a secondary factor, and things like long-term residential segregation based on race and ethnicity could be playing a more important role. When we look at the non-lake versus the lake subset, we see that non-lake still, the risk ratios are all above 1. We do see that flip, right? So we see them flip below 1, which suggests that less vulnerable or disproportionately exposed near lakes, but they weren't significant for the most part. But we do see that flip that has been suggested by the literature, which is focused more on coastal environments. Now, when we break this down by the metros, we can see that, again, generally speaking, all 3 of the risk ratios for each 3 of the metropolitan areas were greater than 1 and statistically significant, which reemphasizes the widespread nature of some of these inequities in urban flood risk. A few things to point out. We saw the greatest ethnicity risk ratio in Atlanta. This is primarily due to the size of the metro area. Some of these greatest inequities were kind of in cities like Canton along the fringes of the metro area. The greatest race risk ratio was in Greenville, Spartanburg. And then Charlotte actually had much smaller risk ratios than the other 2 metros. This is partly due to a coincidence of physical geography, where the more vulnerable communities were actually situated in a area of higher elevation, basically in the stream headwaters. But what this goes to show is that even at that broad scale where you may have favorable physical geography, that still doesn't avoid these inequities at a finer geographic level. Another thing that was interesting is we did see significant risk ratios below 1 for the lake subset in Charlotte. So again, it highlights how water being an amenity in that sense could draw people that are less vulnerable to live in harm's way. But it seems that that connection is a bit more complex for lakes than coastal environments. We can keep going down to more detailed scale for the counties. What I really wanted to focus on here is that if we just look at Atlanta, for example, we see this ring of higher inequities basically around the urban core. And if we add up the amount of significant risk ratios for each of these counties, we see these areas where you have inequities for all three dimensions downwind of Atlanta, where at least downwind during the 2009 Atlanta flood. So we can see in the exact area where we saw this urban enhancement of precipitation from that first example, we can also see this cascading set of vulnerabilities where we have large proportions of vulnerable individuals residing in the area that during that flood event received the most intense rainfall. So kind of a worst case scenario, so to speak. We can go all the way down to the census tract level. We saw less significant risk ratios at the census tract level. That was primarily due to the smaller population sizes, right? Because we're looking at smaller samples essentially. But if we just add up the number of significant risk ratios greater than 1 and compare them to the risk ratios less than 1, so greater than 1, again, that means our vulnerable communities are disproportionately exposed. It's indicated by the green bars here. We can see the green bars typically exceed the gray bars, which are less than 1. So again, even at this census tract scale, we're seeing inequities. Some of the inequities are actually quite large. So as mentioned on that last slide, like 8 times as likely to reside in urban flood zones. And some of the tracts with the largest risk ratios exhibited really stark socioeconomic juxtapositions where you'd have one census block group that maybe is a mobile home park or an apartment complex, and the other census block groups in that tract could be more affluent communities. So this scale really highlighted these stark contrasts over fairly short spatial distances. And what was interesting is when we go in and look at all these individual tracts and what communities they're roughly corresponding to, it seemed like some of these tracts, and particularly the ones for the race risk ratios, are located in these areas that have been historically marginalized for various reasons. So one of the tracts corresponded to the Summerhill neighborhood, which we can see here. So this is the second largest race risk ratio. And it's been historically marginalized for the construction of first Fulton County Stadium and then Turner Field, also marginalized for the construction of the interstates. And it's a really interesting case study that I won't spend too much time discussing, but Atlanta, downtown Atlanta is just off the screen over here to the top left. So this area essentially drains part of downtown Atlanta and is very susceptible to flooding. And we can see that we have minority communities disproportionately exposed to the flooding in this exact region. And since it is so susceptible to flooding, it had a really big flooding event in 2012. It's actually undergoing a stormwater management transformation. So just to give you a sense of what's been happening in these types of locales, the top here is 2010, the bottom's 2017. You can see the big changes that have occurred in terms of displacement. Obviously, you see the permeable pavers, which is part of this transformation project. So obviously, we have implications in terms of, well, we're trying to make this more resilient, but what does that do in terms of gentrification, displacement, et cetera? So it kind of highlights some of those tensions. So what this kind of shows us in terms of the 3 big research questions were, 1, the results were sensitive to the different asymmetric mapping techniques. So it kind of highlights the importance of trying to validate those on an individual study basis because they're likely governed by the underlying geographies of the urban development. We did indeed see that vulnerable populations were between 14 and 42% more likely to reside in areas at risk for flooding. And we saw that across several different scales. So again, suggesting that the issue is fairly widespread and systemic throughout the megaregion. And then based on the comparison of the ethnicity and race risk ratios, and those magnitudes being a bit larger than the poverty dimension, it suggests really that a lot of these environmental justice issues in the region, specifically for urban flooding, are likely due to structural forms of discrimination and residential segregation that have played out historically as these cities have grown. So hopefully that gives you a sense of some of the things I've been thinking about and working on, and how this multi-directional framework in terms of how we look at these human environment interactions and how that can be leveraged to understand urban flooding from kind of a more hydrometeorological perspective, as well as more of an environmental justice vulnerability type lens. So I know I'm running a little short on time, but just to give you a sense of where this is going. So as Brad mentioned, I'm at UT San Antonio now. So really I'm trying to wrap up a lot of my Charlata work and beginning to look at these different dimensions of urban climate and urban climate vulnerability locally here in San Antonio. San Antonio is a really fascinating place to start to explore some of these issues. As many of you probably know, it gets quite hot during the summer. So obviously we have urban heat issues that we need to be discussing and trying to alleviate. We also are located in Flash Flood Alley. So that provides another source of vulnerabilities. And what's interesting about San Antonio is we have like low water crossings where the roads are designed to flood during intense rainfall events, which I've never really experienced before in my time in North Carolina and Georgia. So these are all the low water crossings throughout San Antonio before a rainfall event. And then as it continues to intensify, you can see how lots of these important roads basically become closed at these low water crossing points. So obviously that's a hazard. People drive into them. What can we do about messaging? What actually controls which low water crossings close most frequently? Very interesting to kind of think about how the urban environment is interacting with these natural hazards. Another big ongoing effort that Brad mentioned in the introduction is San Antonio is a bit late to the game, but we're at least proceeding with our climate action plan. And if you're interested in that, we can definitely talk about that more during the Q&A, but a big element of that is obviously urban heat resiliency. So we've partnered with the city to begin to make these urban heat island maps. So looking at the surface temperatures and how they vary spatially. So if you're not familiar with San Antonio, downtown's right here. So this is kind of the Riverwalk. These are kind of the more affluent northern suburbs, and our more vulnerable communities generally reside kind of on the west side, the south side, and the east side. So this arc below downtown, and doesn't take a very well-trained eye to see it's much warmer in these areas south of downtown than these more affluent suburbs to the northwest and northern portions of the city. So as part of this project, we're basically processing a lot of Landsat data to create hundreds of maps like this, to create long-term averages, to look at things like trends, and then ultimately look at some of those vulnerability dimensions as well once we build up the surface urban heat island database. Our campus is actually way out here on the very edges of kind of the suburban sprawl. It was literally in the middle of nowhere when it was first built about 50 years ago, and it's basically become engulfed by San Antonio. And if we zoom in on the city, or on the campus rather, we can see a little bit of a campus heat island as well. So we can see obviously lots of parking lots, since originally UTSA was a pretty big commuting campus and still is to some extent. What's also interesting is you can see the fields are actually even hotter or as hot as the parking lot, since the baseball field is natural grass, which is interesting, and the artificial turf is just exponentially hot on this random summer day in July. So these are some of the kind of detailed variances we're going to be looking at and trying to analyze across the San Antonio metro area. So I'll leave it at that. And I know Brad said, hopefully you guys have some good questions in the Q&A. And just want to thank everyone again for attending today. And thank you all for extending the invitation. I really enjoyed getting to learn more about your department and all the exciting research that's being conducted there. I do want to acknowledge the GWRI, the Georgia Water Resources Institute, which funded some of this work, as well as some seed funding from UTSA, which is supporting some of our ongoing urban heat mapping. So with that, I will stop sharing.
Great, thank you, Neil. If we were in person, we would give you a resounding round of applause, but I'll do it in honor of, or on behalf of the rest of our department. And also at this moment, I want to thank Rachel Ames, who is with our Cosby IT, who has lent us her time and expertise in helping us to set this up. So appreciate you, Rachel, for helping us out. So as we move into our question and answer session, we want to thank Neil for not only the great talk, but we also want to start off with a tradition that we have here in our geography department, where we have our graduate students ask the first question. So the Q&A session, panels method is still open, but if you would like to use the raise hand icon as well, we can unmute your microphone and you can ask your question directly. And I think that'd probably be a good way to start off here, if any graduate students have any questions.
I like that tradition.
Let's see, who's gonna break the seal on this? Any questions from our graduate students?
You can outweight them, Brad. You can do it.
Maybe I can. Maybe I can. All right. While they're formulating their thoughts, Craig, if you have an answer, if you want to go ahead and raise your hand in the chat, then that might give me the opportunity to unmute your microphone. There, perfect. Let's see. And how do I go about doing this?
All right, there you go. How's that?
We can hear you. Hey, Craig.
Perfect. Thank you, Dr. Debbage, for the well said speech, and thank you, Dr. Johnson. So I guess you may get this may be like a running joke for you, but are you more of a physical geographer or a human geographer?
Yeah, that is a tough question for me to answer. I think we had some really good discussions about this with the graduate students earlier today. I think one of the things I really enjoy about geography is the breadth of it, right? Where it makes it very easy to, one, be exposed to these types of ideas, right? If I was in maybe an atmospheric sciences department, I probably would never even encounter environmental justice research, right? That a lot of our human geography colleagues are conducting. But it also lets you kind of explore those interactions between the two. So it's hard for me to really say if it's really one or the other, because I think the interactions between them are really where some of the really exciting things are happening. Now, I guess if you really held a gun to my head and forced me to pick, just based on what I teach as well, I basically teach mainly physical geography. So I guess I'd have to slide slightly towards the physical geography dimension. But again, maybe it's helpful to think about it more as a spectrum and not kind of this either or. Well, of course, they're two kind of spheres, but they overlap to some extent, and perhaps it's a continuum where you can kind of position yourself somewhere along that rather than just focusing on one or the other. So That's a good question, though. You're on mute, Brad.
I see Craig got a follow-up to that where he says, we were also speaking on marketability for postdoc work. As a newer student entering the job market can be difficult. Which would you advise that he leans toward? Going, I guess, directly into a job or pursuing a postdoc? Any thoughts?
Let's see. I'm just trying to read the question. Yeah, we talked a little bit about flexibility when we were talking about the job market and how I had kind of different hats I would put on depending on what application I was applying to, where I could, again, reposition my work slightly more to emphasize maybe the straight up physical geography, urban climate dimensions, or maybe the advert is looking a bit more for someone who is looking more at the kind of the interface of those two things. So I think having some flexibility can't hurt in the sense that it opens up additional opportunities where you're not necessarily pigeonholing yourself in just one very specific sub niche, especially with the competitiveness of the job market and maybe the limited number of kind of opportunities at any given hiring cycle within one specific sub niche. Being able to straddle a few, obviously you can't cover everything, right? But being able to exist at the intersection of maybe two and do a good job there kind of gives you a little bit of flexibility in terms of what you can apply for and what you could ultimately be competitive for. In terms of the kind of postdoc dimension, I mean, I think postdocs are a great opportunity. I never really got to do one, but know people that have and have been pretty beneficial because they help you really just focus on research, right? They give you a lot of time to wrap up dissertation projects and really expand your research agenda and spend a little bit of time that you maybe don't necessarily have during your doctoral dissertation time to kind of get a few more grants and things like that. So I think there's kind of merits there as well.
Excellent. So we have a couple of questions, and I think we have Marcus Williams, Dr. Marcus Williams. He's online. Go ahead, Marcus.
Hey, Neil, how's it going?
Good. You're not a grad student. Why are you asking? No, I'm kidding.
Yeah, I'm glad I'm not a grad student at the time. So I just had a question about some of the wharf flooding work that you did.
Yeah.
Did you stop your runs and your analysis right at the flood event, or did you let it kind of linger on after the flood event ended? Because I'm kind of interested in some of the hydroclimatic responses post flood event, because you mentioned there was excess runoff, greater rainfall. I think that would have some influence on the hydroclimate after the flood event, and like maybe redevelopment of storms around the city or around certain areas. So I don't know if that's something you thought about or something you looked into.
No, that's a really interesting idea. And I don't think with the model run, I probably let it run long enough after the actual event to thoroughly address those types of ideas. But I think that's a really fascinating idea in terms of basically the longer term feedbacks into the climate system, right?
Yeah, I mean, I know some of them might be kind of short term, maybe a day or a week or two, but if you're talking about vulnerability, it might be a flood event or some type of, you have some displacement and then you have hazards after the event. So that might be something,
Yeah, I think that would be really neat to look at. And even, because I think mainly I was looking at, when I ran the model, I put more buffer time at the front end for spin up. And then maybe, I think I have basically like a day afterwards, which could look at maybe some of those shorter term knock-on effects. But I mean, even if you just think about the amount of time it takes for the flooding to subside, obviously you saw in those hydrographs, you have the peaks, but it's not like they go away. And for an event of this magnitude, I mean, it is a long-term kind of hazard until it all flows out and leaves the system. But that does take quite a bit of time. So I'm even thinking about some of the kind of work going on in Puerto Rico at UGA in terms of how those impacts on the landscape have these long-term kind of implications.
Okay, yeah, I was just curious. I know it wasn't the initial aim of your research, but I just thought if you had some thoughts on it or if that was something you were considering.
Yeah, next time I'll let it run longer. That's a good idea. Thanks,
All right.
Marcus.
Thanks, Neil.
Good seeing you or hearing you.
All right, great. Well, let's see. Next up, we have a question in QA from Dr. Sandy Wong, who is one of our experts in our department, assistant professor who focuses on GIS and health. And she's asking, how can your work in Charlata be used to inform local policies and aid high-risk communities?
Yeah, I think that's a great question in terms of what we actually do with this knowledge that we're building, right? I mean, I think outreach is always important. So I've kind of presented some of this at the Chattahoochee Riverkeepers Conference, where it's a little bit different than a typical AMS conference, where it's usually just kind of us talking to one another, right, in the academic community. But attending opportunities like that can be important. And I think this isn't really related to Charlata, but I think that's one of the reasons I was so excited to become involved with the climate action plan here in San Antonio, because that really provides an opportunity to more directly translate some of this research from just papers and articles to something that actually can make a difference in the community. So in a way, I kind of wish I was more involved in the Atlanta Climate Action Plan, but that was created a while ago. So it's exciting to at least be here in San Antonio while that plan it's basically been adopted, but it hasn't been implemented. So be able to guide that process to some extent. So I guess what I'm saying is trying to become more directly involved in the policy arena. So obviously in a lot of papers, you can say, well, planners might read this and this could be helpful, which it could be. But there's also a good chance that planners aren't going to read my papers. So basically bringing myself more to the forefront in those policy areas is something I've been trying to do a bit more since joining UT San Antonio. So I think that would probably be an approach, if I was still in Atlanta, that I would probably take.
Excellent. And while we're waiting for more questions, I can ask a follow-up to that. One of the things that I noticed that your work is pretty multidisciplinary. You utilize tools that were traditionally, meteorology, but you identify directly as a geographer, and that's what your core is, because and rightfully so, you identify with a lot of the breadth within geography. And over the past few years, there's been a growing trend, particularly on moving from multidisciplinary into this transdisciplinary space, where, like you mentioned, we don't talk to one. We've talked to each other quite a lot within the research community, but how do we bring in the actual end users and the policymakers and allow that to influence our research process? Could you talk about what some of your ideas might be going forward with your opportunity with San Antonio, and just in general, and how you envision your work potentially being impacted by what they might need?
Yeah, I think, again, this is part of the challenge with existing in a virtual environment as well, right? I think the networking opportunities are certainly very important. And I was fortunate enough to kind of establish and still working on establishing and growing a relationship with a lot of the city offices. So in particular, the City of San Antonio Office of Sustainability does quite a lot of research on these types of hazards. So we've been able to kind of partner with them and involve them in the research along the way in terms of them actually providing some guidance in terms of what might be useful. So what information do you actually need to guide urban heat resiliency planning? And would it be good to look at longer term versus shorter term? Or what type of spatial analysis techniques do we need to look at to identify inequities and things like that? So I think having a running dialogue with those types of people is pretty helpful in kind of starting it earlier rather than later, right? So again, kind of getting away from this idea of doing it and then giving it to them, but involving stakeholders more throughout the process, I think can be kind of one way to kind of continue that. And it's really interesting with like the Climate Action Committee work. It really is incredibly diverse. So on the committee are people like me that actually kind of study climate change and urban climatology. And there's also people from like the automotive industry. There's people from like CPS, which is our energy provider. So it's really a diverse group in terms of who will be guiding the implementation. So again, kind of putting all our minds together in one place to kind of help achieve something to make San Antonio more resilient. It's kind of the end goal there.
Great, excellent. All right, looks like we have another question from Michael Core, and looks like this is more work specific. How do you come up with the non-urban cropland natural vegetation mosaic? Was it a general mask or was it derived for analysis of the surrounding areas?
Yeah, so that is one of the kind of land uses you can kind of select from WRF. So it's like a pre-existing category, and each of these land uses have different kind of characteristics that the model actually feels, if you want to say that, in terms of surface roughness and all this type of stuff. So that is, the category itself is an existing category. Now, the task in terms of how you get the model to like respect that category is that it was a mask. So essentially going in and changing the pixel values from whatever value in 30 they were. So like 30, 31, 32, something like that, were the urban land uses. And then going in and changing that pixel value in all those urban pixels to the pixel value for the cropland natural mosaic value, which I think was like 14 or something. I can't remember off the top of my head. So that's kind of a little bit more detail on how the masking was done. I actually ended up kind of going outside the urban extent slightly. So kind of selecting some neighboring pixels to ensure all the urban pixels were actually masked out. Now, another interesting thing you can kind of think about is what the alternative land use maybe should be. So I didn't really give this much attention during the talk, but you could, instead of doing the cropland natural vegetation mosaic, you could do things like forest, which could be an alternative. In our case, we avoided that primarily because we wanted to make sure we were capturing surface roughness effects, right? To make sure the alternative also had lower surface roughness than like a forest. So it kind of magnifies the difference between obviously the very rough surface roughness of an urban environment versus kind of flattening it out as much as you can to sum it up fairly simplistically.
Interesting. Okay. And Dr. Elsner is asking, how do you think about your results for a particular city in terms of what might happen in the year 2100 with climate change?
Yeah, that's a great question. And I mean, I think for a lot of these elements, we would anticipate the stress just being amplified further, where from both ends, right? And I think that's one of the themes that keeps coming up is in 2100. It's not just that the climate will be changing and making some of these extremes more extreme and more frequent, but there's a good probability that we'll have more people in harm's way as well. So I think that's kind of part of the reason understanding these things now can be helpful. And again, things like the climate action planning are so critical to be able to kind of address the hazards as they are now to avoid them from getting worse. And not just the hazards, but the exposures and who's being exposed. So I mean, that's a particular challenge here in San Antonio, where some of the federal housing, there's actually no federal requirement that type of housing has air conditioning. There's only a requirement that it has heating, which I actually really didn't know until I moved here. So there's still people living in San Antonio that don't have air conditioning, or maybe they just have wall units, or maybe they do have wall units or air conditioning but can't run them because it's just astronomically expensive to run them enough to keep it sufficiently cool during the summer because of how hot it gets. So trying to think about how we can mitigate that harm will be pretty important.
That's interesting when you think about policy implications and how sweeping policies, you know, like for people in the North or the Midwest, that's a key.
Yeah, it suits those areas, right? But again, since it's the federal level, and it also is applied here, where obviously if you could flip it and make air conditioning required, would probably be more beneficial long term, except for this next week.
Yeah, good luck with that one.
Yeah.
All right, we're on the up in the 5 o'clock Eastern hour, and I'll allow time for one more question, maybe if it comes across. But if while I'm speaking, I want to thank Dr. Debbage for not only sharing your time, but your wisdom, particularly with our graduate students, and taking time to share. And we hope that you all, if you didn't have an opportunity to ask your question today, or you're still mulling on it, you take the opportunity to reach out to Dr. Debbage directly.
Yeah. Certainly, feel free to email me. So my email is just my name at utsa.edu with a period between the first and last name.
Great,
so
perfect.
That's more than happy to converse more offline. So
yeah, so again, well, and I guess we'll go ahead and tie the ribbon on this one then, and let you all go. But we want to thank you for attending our first session of our spring colloquium series. And we look forward to seeing you next time. We have coming up in late April, we have another great speaker who's actually going to focus a little bit more on photogrammetry. And you can find out all about our future speakers by looking at our geography.fsu website under our community and events tab. Thank you again, Dr. Debbage, and thank you everyone else for attending.
Thank you all.